Okay, so now let's move on to the third lecture. So let me just remind you quickly what I did last time. So last time we defined shoot functions in terms of the Cauchy bialternate form, and then we proved this expression for the Cauchy determinant, and using that we showed that the shoot function satisfy this identity where this pi xy is just the product of 1 over 1 minus xi yj. And this earlier we had seen that this implies that the S lambda form an orthonormal basis for the ring of symmetric functions. So today I'm going to prove another formula for the another two formulas for shoot functions, which are due to I believe Jacobi and Trudy. They're called the Jacobi Trudy identity. So I'm not sure if this is historically accurate, but I believe one of them is to be called the Jacobi identity and the other the Trudy identity. So let me just stick with that. But so here's the Jacobi identity. And it says that if lambda has less than or equal to n parts, then S lambda can be written as the determinant of h of lambda I minus I plus j. And this should be regarded as an n by n matrix. So just to give you a feeling for how this works, let's just write down HS31. So the way this works is you write down this matrix. It's going to be a 2 by 2 matrix because this lambda has two parts. And what you do is you write down the lambdas along the diagonal of the matrix. So I'll write H3 here and I'll write H1 here. And that's because when you put I equals J, you just get H lambda I. And then as you increase J, the index on the H increases. So you go to the right and this becomes H4 and this becomes H0. Now here there's a slight caveat. You need to define Hn equals 0 if n is less than 0. So those terms will just not be there. So it's quite possible. So if I had a 3 by 3 matrix, maybe H 3, 2, 1, then the last row would have an H1, then there would be an H0 and an H minus 1, and that would just be replaced by a 0. So anyway, so here what we get is that HS31 is H3, H1 minus H0 is just degree 0. It's a constant polynomial equal to 1 and H4. So that's an expression for S31. So it's very simple in that sense to express shoot functions in terms of complete symmetric functions. And the proof that Mcdonald gives is based on the Cauchy identity. So you say that well, so we have this. I think I've already introduced this notation. I will introduce a formal power series with coefficients in the ring of symmetric functions, and this is ht is some r greater than or equal to 0 hr, and so this is now a symmetric function in variables maybe x or y or whatever, uh, t raised to the power r. So this t is a new formal variable. And this we've seen is given by the product uh, and 1 over 1 minus xit. And it kind of depends on how many variables you're using, what this product runs over. So if you're using infinitely many variables, you just take an infinite product. Otherwise, you take I goes from 1 to n if you're using n variables. And so now if we start with the Cauchy identity, then we have, so that we were calling pi xy, that is product and if we work with say n variables, then we'll have 1 less than or equal to ij less than or equal to n, 1 over 1 minus xi yj. So that's the left hand side of the Cauchy identity. But if you think about what this is saying here in terms of this identity, what this is saying is that we just have a product of I goes from 1 to n of h of yi. because this t has just become maybe I should say j here. Okay, but it doesn't matter. So I'll just write it like this. So this t has become yj, and so you have this. Okay, so now let's try to show. Let's work with this pi of x y a delta. We'll try to show that this is uh, given by. So it's enough to look at this a delta y. So remember, this a delta is the van der Waals determinant. So it's a delta y, and now we're working in n variables. This is going to be the determinant of yi to the n minus j. So this think of this as an n by n matrix. So this is going to be um, summation I equals 1 to n. Sorry, product I goes from 1 to n. And then we have h yi, and then we have summation w in Sn, sine of w times yi raised to n minus wi. And I need to make this a product. So this is also I goes from 1 to n. So we combine this, bring this hi, yi to the n minus wi together, then this becomes determinant of yi raised to n minus j hyi. That's just product in here and merging it with this one. And that you can think of as now expanding out this hyi. I can write this as determinant of summation alpha j greater than or equal to 0 h alpha j, and then we have yi to the power alpha j, but then I will write it as yi, clubbing it with this, I'll get alpha j plus n minus j. I hope that's clear. You expand this determinant, then now so now what is happening here is each row of this, rather, yeah, each uh, so this j, right? So this j corresponds to a column of the matrix. This is an n by n matrix, and we can expand it along each of those columns. I mean, each column is now a linear combination of things, and we can expand all those out. And so what that gives is a sum over alpha j greater than or equal to 0. J is, so this means that alpha 1 is greater than or equal to 0, alpha 2 is greater than or equal to, I think we start with alpha 0, in fact, all greater than or equal to 0. And then we have h alpha is what you'll get from these terms, and then this is in the variables x, just to remind you, and then we have determinant of yi raised to alpha j plus n minus j. Now this is nothing but the numerator of the Cauchy bialternate form for the Schur function. So this is summation over all alpha h alpha. Now here alpha is not running over partitions, but all tuples of n tuples of non-negative integers, a alpha plus delta y. Okay, so that's the expression. So this is not alpha is not a partition. It's running over all tuples of non-negative integers, all integer vectors. So now we need to figure out what the coefficient. So notice that we've already multiplied out by a delta. So if we want to know what this is in terms of Schur functions, we need to know what the coefficient of a lambda plus delta is for any partition lambda. So remember that a alpha plus delta is going to be either 0 or lambda plus delta. So it's going to be uh, plus or minus. So it's going to be epsilon w a lambda plus delta if maybe I need more space for this. Oops. So it's going to be epsilon w a lambda plus delta if um, w if w dot alpha plus delta is equal to lambda plus delta and is equal to 0 if the parts of alpha plus delta are not distinct. So this is a dichotomy because if the parts of lambda alpha plus delta are distinct, you arrange them in strictly decreasing order and you get something of the form lambda plus delta. And so that's the thing. So what you get here is a sum over W belong to Sn. So now you're looking at all H W dot lambda plus delta minus delta. Okay. Internet connection is unstable. Am I audible?
Yes, you are.
Oh, okay, thanks.
No problem.
Okay, so that okay, so now yeah. So that's just determinant of sorry, what is
There is a summation over lambda 2, right?
and so which is just the determinant of h lambda I minus I plus j. So what we're saying is that the coefficient of a lambda plus delta in pi x y a delta y is Jacobi determinant, but then we also have this identity that pi x y is summation s lambda x s lambda y, and when you multiply this by a delta y, then here you get a lambda plus delta y. A dual of this identity called the, which I'll call the 2D identity.
Sorry, can you go to the previous? The whole
Sure.
It's the last.
So this is going to be
Thanks.
yeah, I guess that's correct. Yeah, this is alpha plus delta. So the coefficient of lambda plus delta. That's right. So okay, so that's the Jacobi identity. It just falls out of the Cauchy product expansion in terms of Schur functions. And now the dual is the 2D identity, and this proof I had not seen before. It's a really beautiful proof. So I hope I can explain it clearly, though it's a little bit. So the 2D identity expresses Schur functions in terms of um, um, elementary symmetric functions, and it says that it is determinant of. So let's say suppose lambda 1 is less than or equal to n. So that means that the number of columns in the Young diagram of lambda is at most n. Then we have this e to the lambda prime. So lambda prime is the conjugate partition whose Young diagram, the rows of whose Young diagram are the columns of the Young diagram of lambda. And this expression is the same. Okay, so and here we have to take 1 less than or equal to ij less than or equal to n. So this works very similar to the earlier expression. Along the diagonals, you write down the, I think this should be a lambda prime I. Yeah. So you write down the parts of lambda prime, and then you, as you go to the right, you increase by 1. So here's so this lambda prime is given by lambda prime. That's the notation. And to prove this, we will use a result from the theory of minors of a matrix or determinant theory. So let's first introduce some notation. So you have a matrix. Suppose A is an n by n matrix. I and J are subsets of the set of numbers from 1 to n. And let's say they have the same size. Then we can talk about the submatrix Aij obtained by choosing rows from I and columns from J. And if we write I prime equals the complement of I and J prime equals the complement of J, then the lemma is that if you take A inverse and then you take its ij, so these uh, uh, ij submatrix, and you multiply it by the determinant of A, which is just a scalar, then you get a j prime I prime epsilon I prime. Oops, I didn't define these, epsilon j prime, where epsilon I prime and epsilon j prime are defined as follows. So now if you have this I and j, you can define E. So if I is equal to, so I is the subset of 1 to n, so I can be written as I1 less than I2 less than I, let's say it has k elements, so then you can write it in strictly increasing order. And similarly with j, then you define ei to just be ei1 wedge eik, and similarly ej. So then in particular you have en, the whole thing is e1 wedge en, and this expands the one-dimensional space wedge n of k to the power n, where k is some field that you're working over. So these signs, these are signs, and these are defined by you take ei wedge ei prime, where I prime is the complement of I. So ei wedge ei prime will be first you take all the entries of I and then all the things which are not in I. So it's going to be some permutation of this, and depending on the sign of that permutation, so that's the definition of ei prime. Oops, en I have to say here. And similarly ej wedge ej prime is epsilon j prime en. So that's the lemma, and the proof is not so difficult. It's rather nice. It's one of the reasons exterior powers are so much easier to work with than symmetric powers. So let me just give you the proof, and the proof is as follows. So I want to compute the inverse matrix. I want to compute its ijth, capital I, capital Jth entry. How do I interpret that? That means that I have to take A inverse and I have to apply it to Ej, and then I have to figure out the coefficient of Ei. So just for want of a better notation, I will write the coefficient of Ei in the expansion of Ej in this canonical or standard basis uh, using these inner products. Okay, so that's what the left hand side this expression is. Okay. Now the nice thing about exterior products is that for any uh, tensor V in the kth exterior power of Kn, I can find out the it's easy to find out this coefficient. This is just okay. So the expression is, so you this into En is just epsilon I prime V wedge Ei prime. Why is that? Well, you just take V and expand it in terms of the basis EI and then when you wedge with this, the only term that survives is EI. So if you take EK wedge EI prime, where K and I prime have complementary size, then the only term which survives is where K is the complement of I prime, or in other words, K is equal to I. So this really just picks out the coefficient of EI. And so what we get is uh, A inverse, um, let's say, A inverse Ij n is equal to epsilon I prime A inverse Ej wedge I prime. That comes from this identity up here. So I have picked out the coefficient. This I hope this is clear. This is not in the subscript. Okay, now what you do is apply wedge and A to both sides. Okay, both sides are in the nth exterior power, and so I can apply the nth exterior power of A to both sides. And wedge and A applied to this just gives the determinant, and so you get A inverse determinant, which is the left hand side of what we want with an En, is equal to, and now we get epsilon I prime, and then if you apply this A to here, you get Ej wedge A Ei prime. And that's just epsilon I prime, epsilon J prime. And this is just by using the same formula again, this is going to be the coefficient of Ej prime in the expansion of A Ei prime times En. And so that's just epsilon I prime, epsilon J prime, and this is what we would call A J prime I prime. And so now just comparing these two, you get that A inverse Ij determinant A is epsilon I prime, epsilon J prime, A J prime I prime. You're all familiar with this in at least one special case where I has a size n minus 1, and this gives us the famous rule for inverting a matrix using determinants. So the maybe I and J are singleton. So the ijth entry of the inverse is given by times is 1 over the determinant times this these minors where you leave out one row and one column with a sign. So that's a special case. A inverse ij is minus 1 raised to I plus j over determinant a ji. So that's our rule for inverting matrices. Okay, so now what does this have to do with Jacobi 2D?
Sorry, Amri, just if you go up, what is the notation for A subscript ij?
So A subscript ij is just so what you do is
You take the submatrix.
Yeah.
You have
Hang
to
on.
take
I guess I mean
minor.
yeah, minor of the submatrix.
Okay, now it
Determinant
now,
of the submatrix.
okay, thanks.
Yeah, yeah.
Finally,
So
okay,
sorry,
thank
yeah.
you.
Yeah. Determinant of the submatrix. So it's a minor. Yeah. And that's but wait, I'm sometimes taking determinants and sometimes taking minors, right?
Minor is the
One is
determinant.
minor. This is fine. Yeah, this is fine.
The signed minor is the cofactor.
Yeah. Yeah. So this thing is with these signs, I think this is called the cofactor, right?
Yeah, the last line should have J dash I dash.
What?
Right hand side
That's fine.
matrix of the matrix or J prime I prime.
Yeah.
Yeah, yes.
J prime. Prime. Leave out J, leave out I. So okay, so now what does this have to do with the Jacobi 2D? So let's just look at an example. So already we saw that S31 in the Jacobi form is H3, H4, H0, H1, and in the 2D form it is so we look at 3, 1. So the Young diagram is given by this, and so lambda prime is 2, 1, 1. And so this is given by E2, E1, E1, E3, E4, E0, E2, 0, E0, E1. So this is the kind of thing we want to know. And what we'll do is we will realize these determinants as minors of certain matrices. So the matrices in question are the following, which will be mutual inverses. So now given lambda lambda n with, let's say m is lambda 1. So so well maybe m and n could be greater than, so m could be greater than or equal to lambda 1. It doesn't matter. So let's just do it like this. And so what you do is you consider the m plus n by m plus n matrices. So the matrices I'll consider are H0, H0, H0. So here in our example, we'd be looking at n is 2 and m is 3. So I'd look at 5 by 5 matrices. So let me just do that. H0, H0, H1. So it's a tuplets, upper triangular tuplets matrix. And let's just call this, let's not look at the determinant, let's just look at this matrix. So this is H m plus n. And em plus n will be the matrix with e's instead of h's. but now I'll put a minus for the odd entries and plus for the even entries. Okay, so that's H and E. And what we know, we have this identity, right? That summation H K E to the, how does it go? Maybe I should write H N minus K E K. K goes from 0 to N. And so there should be a minus 1 to the power minus 1 to the power K. This is equal to 1 if N is equal to 0 and 0 otherwise. Now, we know that these upper triangular tuplets matrices multiply just like polynomials. And so this is equivalent to saying that HE is the identity, or in other words, E is H inverse. Okay, so that's one fact that we should keep in mind. And so in this lemma, we are looking at minors of A and minors of A inverse, and we are saying that they are related by something. So let's see if we can find these determinants in here. Okay, so let's look for H3, H4, H0, H1. So I can find it. Let me show you. So I'm going to find its transpose actually the way I'm doing it. So you can also find the H. So this is H3, H4, H0, H1. So the rows I've chosen are 2 and 5. The columns I've chosen. So I have 1, 2, 3, 4, 5. And the rows I've chosen are 1 and 2. And this E, what do I find? So I almost find it. There's some annoying signs, but those signs are not going to be so difficult to control. But let me just show you where it is. So this E is E2, E3, E4. And then we have E0, E1, E2. And then we have here the 0, E0 minus. So it's almost this, but some of the entries have their signs reversed. Now, the sign being reversed is not going to be such a huge problem because the signs are changed on exactly the odd degree factors. And so if you know, and this thing, if you look at this determinant, it's actually homogeneous of degree D. So you know that exactly the sign will be minus 1 to the power D, where D is the degree or the sum of the partition lambda. So let's just make note of the rows and columns here. So here the column numbers are 3, 4, 5. The row numbers are 1, 3, 4, 1, 2, 2, 5. So you see the missing columns, the missing rows here are precisely the columns which we have chosen here, and the missing rows here are precisely the columns that we've chosen here. So this is exactly well, so we need to work out more details, but the point is, so here's a sketch of the proof. And the point is, take A, B, M plus N by M plus N matrices. Maybe I'll call them H and E. I don't know, maybe it's a little as above. And determinant, I'll write down precisely which rows and columns you have to take. Lambda I minus I plus j is is we take H with the rows 1 to what do I want? 1 to n, I guess. And the columns are lambda n plus 1, lambda n minus 1 plus 2, up to lambda 1 plus n. So this is your I, this is your J. And then if you do this, then it turns out that determinant of lambda prime I minus I plus J is H inverse J prime I prime epsilon I prime epsilon J J. So that's the gist of the argument, and of course I guess to check it, it's a bit yeah, I I did my best to check it, but I don't think I can explain it so clearly here, so I'll just leave it at that. Maybe you could work out a few more examples before you get the hang of why it actually works, and there are these signs also to take care of. So that's the proof that Mcdonald gives of the equivalence of it's a proof of the equivalence of the Jacobi and Trudy identities. So it doesn't prove it separately. It just says that, well, if this is this, then that is that. So but a nice corollary of this now from this point of view is that omega of S lambda is S lambda prime for every partition lambda. And the proof is, well, omega of S lambda is going to be omega of, let's use the Trudy form, determinant E lambda prime I plus J minus I. But then this omega is a ring homomorphism, and so we can just take it into the determinant because all sums and products will be preserved, and so that just becomes determinant of H lambda prime I minus I plus J, but that's just S of lambda prime. So this duality comes from the Jacobi and Trudy form for the Schur function. Okay, so let me just pause here and see if there are any questions.
Can I just make a small remark if there's no question?
Sure, please.
I always found it particularly beautiful that this Jacobi-Trudy identity is very closely related to the BGG resolution, or the Jacobi, what you call Jacobi identity.
Mm-hmm.
It writes the Schur function as an alternating sum of homogeneous symmetric functions. And the BGG resolution writes the simple module as an alternating sum of Vermas. And so
it's a resolution of W lambda by Vermas.
Yeah, the simple module for
Yeah.
GLN.
Finite dimensional one, right?
Yeah, the finite dimensional module by Vermas. What about the 2D identity? Do you then that must also, like, you apply then some sort of.
Yeah, the omega is playing the role of a causal duality, if you really
That's right.
think
So you
about
apply
it.
causal duality to the BGG resolution, and I guess in principle you should get, yeah, it's a functor, so you get a resolution of yeah, that's interesting. But then so that would be interesting. So what is the dual of the BGG resolution? Is that easy to see directly?
Well, the standards turn into co-standards and the simples turn into projectives. So
That's right.
you have to do it carefully.
Yeah. Yeah. Wow. Okay, that's nice. Thank you. I think, yeah.
Okay, just on the related note, I just want to know these techniques, the determinant techniques and so on, can be carried over to other types?
Uh,
Is there any good reference for that?
I don't know. Arundam, maybe you have something to say?
Yeah. For classical types, it carries over, and one of the best references is still Hermann Weil's book, The Classical Groups.
Okay.
Okay, so like you're saying that for you may use two variable symmetric functions and so on, right? Get
Well, that's one way to do the proof, but the identity itself is you simply write the Weil character as a determinant of some
right. Okay,
fundamental representation.
yeah. So the other point of view, like the purely combinatorial point of view, I think some of this is there in Sheila Sundaram's PhD thesis,
Yes.
which is very interesting. So,
There is a nice paper of Fulmeck and Krattenthaler where they explain. So I'm just giving the reference in it.
sorry, okay, I didn't catch the name or the first name, but anyway.
Yeah, can you send it in? Okay, thanks.
Okay, so that's good. I see. Okay. So let me move on then. So that takes care of basically whatever I wanted to, the prerequisites from the classical theory of symmetric functions. Now I'll just write down, draw a small table of the various generalizations and what we need to do here, where we are headed, so to speak. So generalizations of Schur functions. So firstly, so I'll make a table. So firstly, we already have seen what we've studied are Schur functions, and okay. So there's another aspect which not decided yet. Maybe I'll try to touch upon in the next lecture. If I give another lecture, I'll just discuss with Arvind exactly how to proceed before I decide on exactly what I'll do the next time. So this but this comes so these Schur functions have an interpretation in terms of zonal spherical functions, and these are zonal spherical functions for the Gelfand pair GLNC UN. So name of the function Gelfand pair, and then I must say what is the inner product. So for the Schur functions, we've seen that the inner product is given by the inner product of P lambda P mu is something into delta lambda mu. So what is that something? And in this case, the something is just Z lambda, the centralizer of the cardinality of the centralizer of a permutation with cycle type lambda, or in other words, product over I to the power mi factorial. And of course, these functions are called S lambda. Notation and other remarks. Okay, so that's what we've looked at so far. And now there are various deformations of these things. So then there's these things called the zonal spherical functions. And these come from GLNR, the Gelfand pair GLNR UN. And these are denoted by capital Z lambda. And the inner product here is 2 to the power L lambda Z lambda. So when I write something here, I'm just saying that, okay, you have to take symmetric functions. Maybe the coefficients are not always just going to be rational numbers. Maybe there'll be something larger. But then what I'm saying is you define an inner product using this formula. And then just as Schur functions are overdetermined by these conditions. So there are, remember that we saw that Schur functions are uh, determined completely by these two conditions. Firstly, that the transition from monomial symmetric functions to Schur functions is triangular. And the second is that Schur functions actually form an orthonormal basis. But this is kind of overdetermined because if you do Gram-Schmidt orthogonalization starting with monomial symmetric functions, you only get this limited set of orthogonalities, but we actually have more orthogonalities. So in that sense, the zonal spherical functions are completely characterized by saying that they come from a triangular transition matrix from the monomial symmetric functions, and that they have the orthogonality property with respect to this deformed inner product. Well, it's not clear that it's deformed from this, but this inner product where p lambda p mu is 2 to the L lambda Z lambda. Okay, there's no nice explicit formula for these zonal spherical functions, but we'll see that they can be obtained by specializations of other things. So then there are Jack's symmetric functions. And these come from GLN of the, I don't really understand this, GLN of the quaternion group and some unitary quaternion. Yeah, some sort of unitary group of the quaternions. And here the inner product is alpha raised to L lambda Z lambda, where this alpha is now a parameter. So you can think of this symmetric functions as living in having coefficients in the ring of polynomials with rational coefficients. Maybe you have to take rational functions with rational coefficients in the variable alpha. And these are usually denoted p lambda. And if you take alpha equals 0, you get e lambda prime. You take alpha equals infinity, you get m lambda. And I guess alpha equals uh, half or 2. 2, yeah. Why did I have alpha equals half? I hope I anyway, maybe I'll correct myself later on. Then you get the Z lambda. So it specializes with these zonal symmetric functions. And then there are the Hall-Littlewood symmetric functions.
Also alpha equal to 1.
Huh? Alpha equals 1. It is Schur functions, I guess. Right?
Yeah.
Hall-Littlewood symmetric functions. And this Mcdonald, so I don't know if there's any they are zonal spherical functions for something. Maybe one of you could correct me. I don't know, but they do arise from what is called the Hall algebra, which comes from the problem of counting subgroups of a finite abelian group of a certain type. And now there's a parameter t, and the inner product is given by product I goes from 1 to L lambda. 1 minus t to the lambda I inverse times Z lambda. And these are usually denoted by p lambda. There's an implicit set of variables x, but then there's this parameter t. And p lambda 0, so I'm removing that x part, is just Schur functions. And p lambda 1 is monomial symmetric function. And then the Mcdonald polynomials. And Arun Ram will tell us what sort of origin here is. And these are given by, now there's another parameter Q as well. And these are denoted by P lambda Q T. And there's a whole phase diagram that Mcdonald draws, which looks something like this. So so maybe I'll just draw that, or maybe I should list the properties here. So let me just list the properties here. So Q equals T, you get sure, and Q equals 0 gives rise to P lambda T, of course. Q equals T to the power alpha gives Jack. T equals 1 gives M lambda for all Q, and Q equals 1 gives E lambda prime for all T. And then there's another very beautiful property which you can check from this characterization, which is that P lambda of Q inverse T inverse is P lambda of QT. Okay, so let me just maybe you can look at this picture, which is in Mcdonald's book that I'm using, and so you draw the Q axis and the T axis, and so this is Q, this is T, and this is 0 0. Let's see, this is 1 0, this is 0 1, and oops, I seem to have yeah. So, and along this you have S lambda, out here you have P lambda T, out here you have M lambda, out here you have E lambda prime, and over here in different directions you get the P P lambda, what do you call them? Yeah, so maybe I should put an alpha here. You can get the P lambda alphas infinitesimally from here. Okay, so these Mcdonald polynomials actually generalize all these symmetric functions that are seen above. And let me just give you a Cauchy identity for the Mcdonald polynomials, which is analogous to the Cauchy identity for Schur functions. So main thing is to define the product. So define pi x, I'll just call it pi for short, and it's got x variables xi, yj, but it's also got two parameters q and t, is defined to be the product over ij. So 1 minus, so this is product r greater than or 0, 1 minus txi yj q to the power r divided by product r greater than or equal to 0, the same thing without it. So this itself is a deformation of the Cauchy determinant. And lemma is that this, in terms of power sum symmetric functions, is equal to, and now this is the deformed inner product thingy, z lambda. Earlier we just had z lambda, now we have this deformed thing called z lambda qt, p lambda x, p lambda y. So this is the deformation of the power sum form of the Cauchy identity over all lambda, where z lambda qt is defined to be z lambda times product I goes from 1 to L lambda 1 minus q raised to lambda I divided by 1 minus t raised to lambda. And the proof of this, well, you take logs, and so you start with this, so log pi, and you manipulate. So this is sum over I j, sum over r, and then we get log of 1 minus t xi yj q raised to r minus log of 1 minus xi yj q raised to r, just note t, yeah. But then you use the expansion for log, so log of 1 minus whatever is minus summation this thing to the power. So you just write it out using the expansion for log. This becomes ij r, and now we have another variable n, another index n, and you just get xi yj q to the power r divided by n, this whole thing raised to the power n. And here there's the only difference in these terms is this t, so I get a 1 minus t to the power n. Okay, that would also be raised. So here you would just get a 1, and here you get a t to the power n. The signs get flipped because it's in the numerator. So that's but then that can be written as summation n greater than or equal to 1, 1 over n, 1 minus t raised to n, 1 minus q raised to n, pnx, pny. And so if you want pi itself, then it's the exponential of this. So it's a product n greater than or equal to 1. And then we have exponentiation of 1 over n, 1 minus t raised to n, 1 minus q to the power n, pnx, pny. And let's see, so what happens to that? That is a product. I'll take this out. And then I will write this, I will expand this exponential. So it's this thing to the power whatever divided by whatever factorial. So I get, let's call that whatever mn. And then I get 1 over mn factorial. And then I get 1 over n, 1 minus t raised to n, 1 minus q raised to n, pnx, pny, mn. And now we'll think of this as a sum over partitions, where the partition lambda is written in exponential notation, 1 raised to m1, 2 raised to m2, and so on. And what this becomes, so if you take p raised to n, product of p raised to n to the power mn, it just becomes p to the power lambda. And this becomes this 1 n to the mn factorial, this becomes z lambda. So what we get is actually sum over lambda 1 over n raised to mn factorial, product I goes from 1 to L lambda, 1 minus t raised to lambda I, 1 minus q raised to lambda I, p lambda x, p lambda. And that's what we wanted to prove. This is just Z lambda QT inverse. Okay, so this is the deformed version of the Cauchy identity, which will work for Mcdonald polynomial. And just a simple corollary with which I'll end is suppose this is the deformed inner product, be the inner product defined by what I had in my table, P lambda P mu is equal to delta lambda mu Z lambda product I goes from 1 to L lambda 1 minus q raised to lambda I 1 minus t raised to lambda I. Then if I have a family of polynomials u lambda and v lambda, suppose these are bases of lambda, the symmetric functions, let's say of degree n, indexed by q. Now we have rational functions in q and t as lambda runs over partitions of n. So if you have such polynomials, then the following are equivalent. U lambda u mu qt equals delta lambda mu for all partitions lambda and mu if and only if sum over lambda u lambda x u lambda y is equal to this y. And the proof of this is actually the same as the proof we had for Schur functions, just using the deformed inner product.
Sorry, Amrit, that should be u lambda v mu and u lambda x v lambda y.
U lambda v lambda. Thank you. Yes. So that's yeah. So that's. I'll stop here for today. I'll discuss with Arvind exactly what I need to do tomorrow. Not tomorrow, next week. So that's it, folks.
Yeah, any questions, comments?
Can we just put one entry into your table, which you, of the Gelfand pairs, because it's, and that's for the whole Littlewood.
Oh,
it's
okay.
GLNQP.
Oh yeah, of course. That's McDonald's whole book. Yeah.
And the maximal compact. Yeah.
Yeah. Thanks. How did I forget?
So they're, because they are all in analogy, GLNR, GLNH, GLNQP.
Okay. Oops. Yeah.
In the specialization of Mcdonald to Jack, you said it in the figure, but in the let t go
Yeah,
to 1
q equals t to the power alpha.
and t go, then t go to 1.
So then you and then t, yeah, what is it? T equals
Then
1.
you let t go to 1.
Yeah.
That's what you've
Sorry.
drawn in the figure.
Yeah, yeah. Is that exactly what McDonald's? So I don't really understand this. I mean, I haven't looked at it so carefully, but I just copied it down from McDonald's. So I could have.
Yeah, I mean, that's exactly what you have said.
Is correct?
Yeah.
Okay.
I mean, in your figure also you have said, right?
Yeah, yeah. But I was a bit vague there. So McDonald has exactly the same figure in the book. I just copied it.
Sorry, can I just write down the last statement as well? The very last lemma, the corollary.
Yeah. Why you don't have to write it down.
It's fine. It was X and Y. Fine. Just checking. I mean, or it could be.
Yeah,
the-
it's the
Yeah.
exact analog of
Yeah.
the.
Right. Thanks.
I don't know. It's somewhere up here. In lecture 2, I think.
Yeah.
Right. We had.
Okay, if there are no more questions, let's thank Amri. I'll stop the recording.